All right, we're going to continue our our time looking at double integrals, and now we're going to look at doing a double integral over a region that's not a rectangle but some other shape. So we'll just start this off with an example, and we'll talk through it. Okay, so let's take the integral over this region D, the integral of x plus 2y dA, where D is bounded by these two different parabolas. Y is 2x squared and y is 1 plus x squared. So this is what the region looks like. You can see that it looks like some smiley face of like a crazy person. But anyway, so how we're going to do this is we need to figure out, we need to kind of set the bounds in terms of the variables. First, we have to figure out, what are these intersection points. We need to know that. Now, it actually is pretty straightforward from the graph. You can check it pretty easily that x is going to be in the range of -1 to 1. You can just plug in -1 and you'll get the same y value for both of these functions. So it seems like we want x to be between -1 and 1, but we don't want y to go all the way between two constants. Y is going to have variable bounds, and so we're going to kind of think of this in terms of a bunch of little a bunch of little rectangular regions that in a Riemann sum is going to limit to be this. Right? You can picture that now. So we're going to set up the integral with the constant bounds for x on the outermost iterated integral. So I'm going to write it like this, and the next layer is going to be the y bounds. Y is going to be bounded by a lower function. This lower function is y equals 2x squared. And the upper function is y equals 1 plus x squared. So we're going to put those bounds, 2x squared and 1 plus x squared, as the bounds on our innermost integral. We're integrating x plus 2y dy. So we're going to now proceed to do this integral. So we're going to integrate, I'm going to keep the outer bounds, but I'm going to integrate with respect to y. We're going to get xy plus y squared, and the bounds 2x squared and 1 plus x squared. Just as we would with a definite integral, we're going to evaluate this at the upper bound minus the lower bound, but now we're going to have some x's that are popping up. So the with the upper bound 1 plus x squared, it's going to be x times 1 plus x squared plus 1 plus x squared squared. So I'll say this is like this antiderivative evaluated at the upper function bound minus this thing evaluated at the lower one, which is going to be x times 2x squared plus 2x squared squared. And this is, there's a little dx. I'm going to clean this up a little bit. We have x plus x to the third plus, let's see, 1 plus 2x squared plus x to the fourth minus, and these are all going to be negative, minus, that's going to be a 2x to the third minus, that's going to be a 4x to the fourth dx. So actually we can just tidy this up a teeny bit more. We have negative 3x to the fourth, that's the x to the fourth. So we have x to the third, that's the x1 minus 2, that's minus x to the third. Those are done. We have plus 2x squared plus x plus 1 dx. All right, let's evaluate this thing. And so we're going to get negative 3/5 x to the fifth minus 1/4 x to the 4th plus 2/3 x to the 3rd plus 1/2 x squared plus x. And we're going to go from -1 up to 1. So we're going to have this evaluated. Let's see, we're going to have -3/5. I guess one thing you could do is you could since we could take the odd parts, separate it as the odd. Yeah, let's just let's just do it. We have -3/5 minus 1/4 plus 2/3 plus 1/2 plus 1 minus, we have, when you plug in -1, you're going to have minus +3/5 minus 1/4 minus 2/3 plus 1/2 and then minus 1. So we'll see what we get for this. We get -6/5 plus 4/3 plus 2. We get 32/15. Okay, cool. So what we did there, we're going to continue to do. We have to look at the region, figure out which of the bounds can be constant bounds, and that has to be the outermost integral. All right, so now we're going to find the solid, find the volume of the solid that lies under z equals x squared plus y squared above this region D given by these two bounds, y equals 2x and y equals x squared. Here I'm going to just sketch it out because it's simple enough. So this is the region D. We have one is this parabola. Oh, this is sloppy. And then y equals 2x is going to intersect here, and I also know it's going to intersect up there. Okay, so it's this little sliver. Now I want to figure out what is the constant bounds and what's the variable bounds. And you can see that as x goes between 0 and 2, the lower bound is going to be this function x squared, and the upper one is going to be 2x. So it's like you're making a lot of these little vertical lines. So that's exactly how I'm going to set this up. We're going to integrate from 0 to 2 in terms of x. But for y, the lower bound is going to be x squared, upper bound is going to be 2x, and the function I'm integrating is this surface, oops, not z, well it is z, but x squared plus y squared dy. All right, so we'll take the inner integral, and this is going to be integrated with respect to y. We're going to get an x squared y plus 1/3 y to the 3rd. Okay, and then the lower bound is x squared, upper bound is 2x. And we have to now just plug this stuff in. So when we plug in 2x, we get x squared times 2x plus 1/3 times 2x to the 3rd minus x squared times x squared minus 1/3 x squared to the 3rd dx. So we'll clean this up a little bit. Let's see what we have. We've got 2x to the 3rd plus, that's going to be 8/3 x to the 3rd minus x to the 4th minus 1/3 x to the 6th. Now, I could combine those two fractions, but I kind of rather not, so let's not bother. Okay, let's do the integral of this. So we're going to get x to the 4th and then bring a 1/4, so it's going to be 1/2. That's 2 divided by 4. Plus, it's going to be and bring a 4 down there, so it's going to be 2/3 now, x to the 4th, minus 1/5 x to the 5th, minus 1, that's going to be 1/21 x to the 7th. And we're going from 0 to 2. And the nice thing about the 0 is that all we have to do is plug in 2 and we'll get our answer. So it's going to be 1/2 times 16, that's 2 to the 4th, plus 2/3 times 16, minus 1/5 times 32, and then minus 1/21 times, let's see, 32, 64, 128. Yep, and so we're going to get 216 over 35 for our volume of this solid. All right. All right, let's take a look at this one. We want to evaluate this integral of xy dA, where the region D is bounded by y equals x minus 1 and y squared equals 2x plus 6. So this is a picture of the region D on the xy plane, and you can see the points here that we have intersections. You can calculate this, but you can just trust me that they intersect at 5, 4, and at -1, -2. And so if you observe, if we were to do the same thing we were doing before, where we have x going from, if we had x going from -3 up to 5, we'd have the lower function be actually changing halfway through. The lower function would be a line over here, but over here would be this parabola. Instead, let's consider horizontal kind of segments. You can see when we slice it up in this way, the lower function is here, and that's going to be actually, we would write this parabola. If we solve it for x, we get let's see, 2x equals y squared minus 6. That's going to be x is equal to 1/2 y squared minus 3. So that's actually x equals 1/2 y squared minus 3. And then this here, if we solve this line for x, we get x equals y plus 1. So what we're going to do is have our y value go between 4 and -2 and 4. -2 to 4, this is going to be our y's, our dy. And then we're going to have the bounds on x are going to be variable bounds functions of y, where the lower bound is this is the lower bound on the left, because that's like the negative side. That's the lower side of things. It's 1/2 y squared minus 3. The upper bound is y plus 1. xy dx. So we're gonna take care of this now. -2 to 4. Integral of xy with respect to x, well, it's going to be 1/2 x squared y from 1/2 y squared minus 3 up to y plus 1. Now we have to evaluate. We have 1/2 y plus 1 squared y minus 1/2 y, another 1/2 y squared minus 3 squared y. And then we have dy. Clean this up a little bit on the inside. We're going to have this integral from -2 up to 4. This inner expression, when you clean it up, you get, okay, so I factored out the 1/2, and so we've got this expression, -y to the 5th over 4, plus 4y to the 3rd, plus 2y squared minus 8y, okay, dy. We can go ahead now and just evaluate this thing. So we have 1/2. This is going to be negative y to the 6th over 4 times 6 is a 24, plus 4y to the 4th over 4, well, that's going to just be y to the 4th, plus a 2/3 y to the 3rd, minus 8 over 2, that's going to be a 4y squared, from negative 2 up to 4. And just take your time and work that thing out, you're going to get a 36. All right, cool. All right, now let's try to find the volume of a tetrahedron. This is a tetrahedron that is bounded by 4 planes, as all tetrahedrons are. And it's probably, well, notice that one of the planes is z equals 0. That's the xy plane. Let's take a look at what this, we can graph the other stuff on the xy plane. Well, we have x equals 0, so we have one bound is just the y-axis. Then we x equals 2y. That's, in other words, that's y equals 1/2 x. That's going to be this line, y equals 1/2 x, or x equals 2y. This is x equals 0. Now we have this other plane, which is x plus 2y plus z equals 2. I'm actually going to take this and I'm going to rewrite that as z equals negative x minus 2y plus 2. Now this plane is, well, so far these two planes have been kind of vertical in the z direction. And so this plane is going to intersect the xy plane somewhere. Let's see where it intersects the xy plane. Set z equals 0. So negative x minus 2y plus 2. Let's just write this as, put the 2y on the other side. We have 2y equals negative x plus 2. Y is negative 1/2 x plus a 1. Okay, so it intersects at 1, and it has a slope of negative 1/2. That's y equals negative 1/2 x plus 1. All right, and so then if you kind of picture this in 3 dimensions, we have some, this is coming up into the air a little bit. So that's the picture you have in mind. It's not this what I just drew is a 3-dimensional kind of perspective. So okay, now we want to think about how we want to split up this region on the xy plane, and it's clear to me that if you slice it horizontally, your lower bound and upper bound are going to not be the same the whole way across. See, my upper function is changing halfway through. Instead, if I do this with vertical slices, I'm going to have the same upper function, the same lower function the whole way across. What's this intersection point? Well, it should be pretty clear here, because it goes down by 1/2 for every 1 unit across. This line goes up by 1/2 unit every 1 unit across, so it's actually at 1. So I'm going to set this up where x is going to go from 0 to 1, and y is going to go from negative 1/2 x. I'm sorry, the lower bound is just 1/2 x, and the upper bound is negative 1/2 x plus 1. I'm trying to find the volume of this thing, and the volume is found by just integrating the number 1. And so then what is I'm trying to find the volume that's the volume under this plane over this region. So I'm going to have that as my function. I'm integrating negative x minus 2y plus 2 dy, the iterated integral. All right, first integral, we're going to Integrate with respect to y, so we're going to have negative 2x of negative xy minus y squared plus 2y, and we're going from 1/2 x up to negative 1/2 x plus 1 dx. Okay. So this, I'm gonna bring it down over here. So let's see, we have negative x times negative 1/2 x plus 1 minus negative 1/2 x plus 1 squared plus 2 times negative 1/2 x plus 1. Now we're going to, it's going to be minus negative x times 1/2 x minus 1/2 x squared plus 2 times 1/2 x. And this whole thing is going to be another set of parentheses dx. All right, I'll save you the pain of cleaning up this mess in the middle. What we get is integral from 0 to 1 x squared minus 2x plus 1 dx, and this is going to be we get 1/3 x to the third minus x squared plus x from 0 to 1, which is just going to be 1/3 minus 1 plus 1, so it's just 1/3. Incidentally, if you realize something, you could have actually done this without doing the integral. If the height of this is, if you plug in x and y equals 0, you're going to get a height of 2. So what we have is we have a triangular base. I'll try to put it in the in terms of the xy plane. We have this is this base with a height of 2. The area of the base is 1/2 base times height, so it's actually 1/2 times 1 times 1, and so the volume of a pyramid, which is what this is, it's 1/3 base area times height, which is 1/3 times 2 times 1/2. So it comes out to be 1/3. Saves a little time if you know the formula, but this is just showing how. I mean, you could do this with much more complicated shapes, of course. All right, let's take a look at this one. Now we're asked to evaluate this double integral where it looks like y is going from x to 1, x is going from 0 to 1. Let's try to graph this thing out and see what this looks like. So x is going from 0 to 1. Y is going from this, so this would be the line y equals x. That's a diagonal line. Okay, and up to 1. So the y values would be, so this is the triangular region that we're dealing with. But I want you to kind of observe that this is actually the integral of the sine of y squared is not pretty. What's going to actually make a lot of, it's going to help out if instead of doing the integral in this order, if we integrated with respect to x first. So instead we're going to have y going from 0 to 1, and x is going to be going between these two bounds, where this is of course 0 and this is y. So I'll show you what I mean. This is equal to the integral from 0 to 1, that's the dy, and then the lower bound function would be 0 and the upper would be y, the sine of y squared dx. Okay, so here's the reason why this is going to be better. So this is going to be integral from 0 to 1 the integral of sine of y squared, because there's no x's involved, it's just going to be x times the sine of y squared, right? And I'm going to be going from 0 to y. Remember, y is not my variable yet. Y is constant. So I'm going to be just getting integral from 0 to 1 of y times the sine of y squared, dy. So I can do a little bit of a substitution here. Let u be y squared. du is 2y dy. And so y dy is 1/2 du. And then changing these bounds, the bounds are still going to be the same. When y is 1, u is 1. When y is 0, u is 0. So this is going to be the integral from 0 to 1, but a 1/2 comes out of this because I'm going to du. The y dy becomes 1/2 du. 1/2 du, and then I have the sine of u. Okay, this is 1/2. The integral of sine, remember, is negative cosine of u. And from 0 to 1, this is going to be 1/2 the negative cosine of 1 minus the negative cosine of 0. Well, cosine of 1 isn't anything special to speak of, but I know the cosine of 0 is 1. So this is minus a minus, that's plus. That's going to be plus a 1. So in the end, this thing is 1/2 1 minus the cosine of 1. So that's what it is, whatever that comes out to be, some number. So now we're going to just list off some of the properties of double integrals. These can help you evaluate them more easily sometimes. So first off, that they're separable by addition. So if you have a function of xy plus a function of g of xy, the integral of this would be the integral of the f plus the integral of the g. This is the same property that you have for regular integrals. Okay, secondly, if you have a constant scalar in there, constant factor, you can just pull that straight out of the integral. That's not going to change the answer. So constants can be factored out. Okay, next, if we know that the function f is always greater than or equal to g for any points in this region D, then the integral over d of f will be greater than or equal to the integral over d of the function g. So if d can be partitioned into d1 and d2, that is to say your region D is here, if you can split it into d1, d2, then the integral over d of f of xy dA is going to be the integral over d1 f of xy dA plus the integral over d2 f of xy dA. Okay, and then you could, if you split it, partition it into multiple little subregions. Remember, partition is non-overlapping and complete, so there's nothing left out. That's what a partition is. So if the function is bounded below by little m and bounded above by big M for all xy in the region D, then m times the area of D is going to be less than or equal to the integral over the region D of f of xy dA, and that's less than or equal to big M times the area of D. So these are some properties of double integrals. We'll be doing a lot more practice, but essentially what it comes down to is looking at the region, figuring out which variable is better to give it constant bounds, and which variable should have function bounds, where the function is that other variable that was given constant bounds. Then you have to put them in the right order, and you'll be fine. Okay, bye.